Hi, my name is Tim Middleton. I'm a software engineer with the Coherence development team here at Oracle. Welcome to this screencast which covers an overview of the Coherence Operator. In this video we'll provide an introduction to the Coherence Operator as well as show you a demonstration of some of the capabilities. What is an operator? An application-specific controller that extends the Kubernetes API to create, configure and manage instances of complex applications. The Coherence Operator is an operator that allows users to create, configure, and manage coherence clusters within a Kubernetes environment. What does the Coherence Operator provide? The ability to easily deploy, run, and manage coherence within a Kubernetes environment. Provides integration with common components used in Kubernetes, Elasticsearch, Fluentd, and Kibana for log capture and analysis, and Prometheus and Grafana for metrics and monitoring, which is available with an imminent 12.2.1.4 release. It allows you to override and customize your coherence deployments, allows safe scaling out or in via Kubernetes with no data loss, provides access to cluster via Coherence Extend, ensures coherence is aware of Kubernetes zones to provide coherence cluster high availability, allows you to use persistence volume claims to support active persistence, and provides application code deployment via sidecar containers. Coherence is installed on Kubernetes using two Helm charts. The Coherence Operator is required and should be installed before installing any other components. The operator understands the resiliency of the underlying Kubernetes cluster and can be configured to install additional components for monitoring and log capture. The coherence chart is installed using Kubernetes stateful sets, which allows features such as persistence and safe rolling upgrades, scale in or scale out, to be carried out. 1.0.0 of the operator uses coherence 12.2.1.3.2 by default. You can change the coherence image and hence the version if required when installing. For application deployments, the user builds a sidecar container with resources such as jars and configuration files included in well-known locations. This sidecar is deployed and referenced in the Coherence Helm install, and resources are added to the class path of Coherence container at runtime. Application containers can be updated safely via rolling update, which ensures no data loss. The stateful set can also be scaled via kubectl. In this demonstration, we will install the Coherence Operator and coherence charts as well as access the cluster via kubectl. We will also install the Coherence demo application. This will show the usage of the sidecar image for application artifacts such as configuration files and domain classes. It will also show the scaling of the storage tier as well as carrying out a safe rolling upgrade of the sidecar image. In the first part of this demonstration, we will show how to install the coherence cluster using the Coherence Operator and then access the cluster via kubectl. We'll use the following Helm command to install the Coherence Operator. The operator should be installed before any coherence components are installed. We are setting the name of the release, the namespace, and the target namespace for monitoring. For this demonstration, we are running against Oracle's Container Engine for Kubernetes, or OKE, on Oracle's cloud infrastructure. You can also deploy this against any cloud Kubernetes engine meeting the Coherence Operator minimum requirements. The coherence Docker images for the operator are available on Docker Hub and will be pulled automatically as required. When a Helm chart is installed, the result is a release. We can use Helm ls to view the installed releases. We can also use kubectl get pods to list the pods that make up the release. Under the Ready column, we can see the number of containers in the Coherence Operator pod and the number of containers that are ready. The operator container implements a readiness probe to let Kubernetes know when it is ready to receive traffic. Now that the Coherence Operator is installed, we will install Coherence with a cluster size of 3. The above command also sets the namespace we're installing into as well as a secret to be used by Kubernetes cluster to pull any required Docker images. In this demonstration, our secret contains the credentials for the Oracle Container Registry where the coherence image is available from. To use and pull this image requires accepting of Oracle's terms and conditions. Once coherence is installed, we can use Helm ls to view the releases. Under the Ready column, we can see the number of containers in the coherence pods and the number of containers that are ready. The Coherence container implements a Coherence specific readiness probe to ensure all services are ready and meet a status HA check. Let's requery the pods. We can see the pods are now ready. If we describe the pods, we can see that each one is spread across different Kubernetes zones for high availability. On OCI, these are referred to as availability domains. This is achieved via the operator's understanding of the underlying zone information and ensuring the best backup strength for the cluster. Next, we will port forward the Coherence Extend port, which will allow us to connect into the cluster and add data. Normally, a load balancer would be used, but we are just using a simple port forward for this demonstration. Next, we will run kubectl and insert data across Coherence Extend to the cluster. We can successfully insert and select data from our cluster. For the next part of the demonstration, we're going to deploy the Coherence demo application, which comprises of a storage tier and application tier. This is a typical Coherence deployment, where the storage tier stores application data, and the application tier is storage disabled and contains application code. Both tiers can be independently scaled. For this, we need to create and deploy a sidecar image, which will be attached at runtime and includes any Coherence configuration and domain classes required by the application. We have already created and pushed our sidecar image to a location available to the Kubernetes cluster. In this example, it's my Docker IO repository, but would usually be a private Docker registry. We will start off with version 3.0.0 snapshot of the image and issue a rolling upgrade of this image later. Firstly, we are going to install the storage tier. In this Helm install example, we are using a YAML file to contain our options to be sent to the installer. Notice that the user artifacts image points to version 3.0.0 snapshot of our sidecar image. We are also setting various Coherence specific options such as the cache and POF configuration as well as the operational override file. For this example, we are just installing a single storage tier pod which we will scale later on. Next, we will install our application tier which contains our Grizzly server and application code. The main difference with the YAML file for the application tier is that we are installing it as storage disabled and ensuring we use a well-known address that connects us to the storage cluster we just created. Once the application tier is started, we will port forward the application HTTP port so we can access the Coherence demonstration application. The Coherence demonstration application adds random stock price data, continuously queries the cluster for this information, shows the time taken to query, and shows the data distribution amongst the members. As mentioned before, there is currently only one storage tier pod. We will use the kubectl scale stateful sets to scale the deployment to 3 nodes. We can now see that 2 additional nodes are started and the UI shows the data distribution amongst the nodes. You will note that the new servers have much higher member numbers than the original member. This is because in 12.2.1.3 the liveness probe joins as a Coherence cluster member each time to check the pod state. In 12.2.1.4 this has been changed to use management over rest. Let's take a note of the number of positions and the approximate quantity and value. Next, we are going to issue a rolling upgrade to the user artifacts image to 3.0.1 snapshot. The image has a new server-side interceptor that will double the quantity of trades inserted per position and hence double the total value. The key takeaway from this command is that we're updating the user artifacts image to 3.0.1 snapshot. Because we use stateful sets, we will see the pods being upgraded one by one to the new user artifacts image. After each pod is upgraded, the cluster is checked to ensure that it is safe to continue, and if so, the next pod proceeds. We can view the progress of the Helm upgrade by using the following command. This command will exit when all pods have been upgraded. Also, if we view the Coherence demo application, we can see that the number of members is changing. During the upgrade, and when the upgrade is complete, you will see that all trades are still present and the totals match. This means the upgrade was done in a safe manner and did not result in the loss of any data. Now that the upgrade is completed, let's note the approximate value of the positions. 49 million and approximately 999 million. We'll remove all the data and re-add new trades. Because the rolling upgrade has been completed, we see that the quantity and value is approximately doubled due to the new server-side interceptor being applied from 301 snapshot of the sidecar image. If you would like more information about the Coherence demo app, please go to the Coherence community at coherence.oracle.com. This concludes the demonstration. If you would like more information about the Coherence operator, please visit github.com/oracle/coherence-operator. You can also view the Coherence operator documentation and detailed samples available at oracle.github.io/coherence-operator. Also, feel free to join our operator and Coherence channels on Slack by using the instructions in the documentation. Thank you for your time.